Okay, so here's where we left off. We are trying to approximate the signed volume that we get when we attach a height, determined by a function f, to this globular region, which is the image of this lovely rectangle in the UV plane. So, we've said that the signed volume will be approximately the height times the area of the base. We approximated the height by our usual just go into denial and pretend the height is constant. Okay? Now we need to approximate the area of the base. So what we had determined was that this globular region was going to have approximately the same area as this parallelogram, where what we did was we took the vector that was tangent to this blue curve at this particular point, and that was going to be the partial derivative of our transformation t with respect to u. Because along this curve, u is the only variable, we're holding v constant. We said this was a constant v curve. Okay? And then we took that and we scaled it, because we said this would be the length that we would expect to get if we allowed u to change by 1 full unit. If we're only allowing u to change by delta u, we're going to scale the whole thing by that amount. And then we did the same thing for this green side. Along the green curves, v is changing, but we're holding u constant. So the vector that points in the correct direction, that would be tangent to that curve, is the partial of t with respect to v, evaluated at u star v star. And again, we scaled that by the amount that we allowed v to change, by our delta v. All right, so now we just have to remember how to find the area of a parallelogram in 2 space. So if you said take the cross product, you are making up math. We can't take the cross product in 2 space. Now, one option would be to embed this in 3 space and then take the cross product of the resulting vectors. But we actually learned something in 2 space, ages ago. We learned that if we're in 2 space, and I have a vector A and another vector B, and I want to calculate the area of that parallelogram, the area of the parallelogram is the absolute value of the determinant of the matrix I get by basically putting A and B in as the columns of my matrix. Turns out I can actually put them in as either the rows or the columns. I get the same determinant either way. For a reason I'll explain in a bit, I actually want to put them in as the columns. Okay. So what I need to do is describe these 2 vectors component-wise. They are in 2 space. They're in the xy plane. Put those vectors in as the columns of a matrix. Take the determinant of that matrix, and then take the absolute value of that. Okay, so let's see. What does the partial of t with respect to u look like? Well, it's just going to be the partial of x with respect to u, comma, partial of x with respect to v. Because remember, t was this function whose output was 2-dimensional. So it was giving me an x value and a y value. Okay. So we're used to sometimes a derivative having 2 components like this. This is now just a partial derivative. We're sort of putting together a lot of stuff. And the partial of t with respect to v, very similar, is going to be the partial of x with respect to v, comma, partial of y with respect to v. I'm used to writing these things as rows, because that's how we've usually written them, but I'm going to put them into a matrix as columns. Okay. All right, and let's see. I want to remember that I'm evaluating these at this point, u star, v star. Okay. So, what I will get is that this area is approximately the absolute value of the determinant. Let's just calculate the determinant of partial of t with respect to u as the first column, partial of t with respect to v as the second column, and then we'll take the absolute value of that. Okay, so here I'm just doing part of the process, just taking the determinant. Okay, so that's going to be the determinant of partial x, partial u, partial y, partial u. I wrote this wrong. I'm sorry. The second one here, you know what? I'm just going to redo this. Because I can and I want to. So I'm going to go and upload those two, and then we'll do that one.